Hello, 8th grade. Today we're going on to the next chapter, or the next section of chapter 4 in our science books. We are going on to work and energy. And so we're going to start talking about force and friction and movement, momentum, as we dig into this next section. So we are on page 230 in your science book. 4.2.1, titled Work and Energy Defined. So, objectives of this chapter: to correlate the terms force, motion, work, and energy, to calculate the amount of work done when given force and distance, distinguishing between potential and kinetic energy. Vocabulary: energy, the ability to do work; kinetic energy, the energy contained in moving objects; potential energy, the energy that is stored by way of object's position, chemical makeup, or elasticity; and work, the measure of energy transferred when a force is applied to an object that causes it to move, and at least part of that force is in the direction of the movement. Words used in science are oftentimes the same words used in everyday language, but the definitions can be vastly different. The word work is one of these words. You may work hard to study for a test or to plan a science project. When you work as a babysitter, you might watch or check on a sleeping baby. A counselor's work includes taking and listening to people all day, or talking to and listening to people all day. Someone might work long and hard, but unsuccessfully, to push open a stuck door. The word work is used to describe these different scenarios, but according to scientists, these situations are ones where no actual work is being accomplished. In science, work is the measure of the energy transferred when a force is applied to an object that causes it to move, and at least part of that force is in the direction of the movement. You may do a lot of thinking when you're doing your homework, but according to scientists, you have not done any work because you have not moved an object. A person may exert great force trying to push a broken down car, but unless that car actually moves, no work has been done. If you lift your backpack 2 meters, you have done twice as much work than if you lifted it 1 meter. But if you hold your backpack for 20 minutes, you have not done any work, no matter how heavy the backpack is. When you walk down the hallway while wearing your backpack, you are not doing work on the backpack because the force of the backpack is upward, but the motion is forward. The amount of work can be calculated by using the following formula, assuming that the force is constant. W equals F times D. In this formula, W is the work done, F is the force in newtons, and D is the distance the object moved in meters. Only the distance traveled in the direction of force counts. The unit for the product of newtons and meters is the Newton meter, Nm, or the joule, J. A kilojoule, kJ, is 1,000 joules. Doing work requires energy. In fact, energy is defined as the ability to do work. You cannot do work without using energy, and you cannot give anything energy without doing work. The two go hand in hand. A car gets its energy from gasoline. When it runs out of gas, the car stops and no longer has energy to do the work of overcoming friction. Animals get energy from the food they eat. When they have used all the energy from the food they have eaten, they must eat again. You can see in the chart on page 230, it kind of gives you examples of work before we go on to the next page. So examples of doing work. So a woman picking up a basket of laundry, the direct force is picking up, but the direct motion is in a different direction. And so that's actually not considered work. Outside of scientific terms, I would beg to differ that folding laundry is work. Someone pushing a dolly with boxes on it, your direction of force is forward and the direction of movement is forward. They're both going in the same direction, and so this is considered work. Same with sweeping. You're at a downward slant, but moving in the same direction. And so, yes, that would be considered work. And then climbing, rock climbing, the direction of force is up and your direction of movement is up. And so, therefore, that is considered work. Try this. Tabletop bowling. Set up dominoes in a triangular configuration similar to bowling pins. Create a bowling lane with the edges of books. Take turns rolling a marble down the lane to knock over the dominoes. Is any work being done? And explain. Identify all instances of potential and kinetic energy. So, if there's force moving the marble forward and it's moving in the same direction as the force exerted on it, is that considered work? Laws and principles. Work. If a girl with a mass of 40 kilograms climbs a vertical ladder that is 5 meters high, how much work does she do? So here's where the formula comes into place. Find the weight of the girl in newtons. And so first, 40 kilograms times 9.8 meters per second squared, that was our formula from before, equals 392 newtons. So that's her weight or her mass in newtons. Then we find the amount of work the girl did. So F times D equals W, work. 392 newtons is the force. 5 meters is the direction that it went in. And then your work is equal to 1,960 joules. The girl used 1,960 joules of energy to climb the ladder. 1,960 joules of work. Energy can either be kinetic or potential energy. Kinetic energy is contained in moving objects. Objects with kinetic